Okay, so in this video, we want to go over an example with a voltage-controlled current source, and we want to solve the power dissipation and delivery in every element in the circuit and check the current everywhere. So looking at this problem, we have an independent current source here, 1.5 amps, and we also have a dependent current source here of this nasty mess of stuff, 2/3 ohm minus 1 times Vx. When you first look at this problem, it looks just disgusting, I guess, because of this, but it's really not that bad. So all we need to do is we need to figure out what the voltage drop is across this resistor, because that's what this current source depends on. And once we get that, we multiply it by this stuff, and then we're good to go, and we can solve the problem just as if it was like a regular current source. So to get started, let's find out what Vx is. This is our controlling voltage. And it's actually quite simple. All we need to do is write V equals IR, Ohm's law, because we actually have the current. We know that because of this independent current source that 1.5 amps has to be flowing through here. And we also know that the resistance is 3 ohms. So this is just 1.5 amps times 3 ohms, which is 4.5 volts. Now we know that this is the positive side and this is the negative side because of the passive sign convention. I'll put a link to the video I did on that in the top right corner. You can check that out if you want, but otherwise we'll keep going. So now that we have Vx, all we need to do is substitute it into here. So Vx is equal to 4.5 volts. Maybe let's even draw this on here. We know it goes like that. It's equal to 4.5 volts. So 4.5 times 2 divided by 3 is going to give us a current of just simply 3 amps. And the units check out because if we were to rearrange Ohm's law here for I, we'd have voltage, which is in volts, divided by resistance, which is in ohms. So volts divided by ohms gives us amps. And here we have volts divided by ohms, because this is just an inverse. This can just be like on the bottom. So that's going to give us amps. So really, when you see something like this, it's actually not that bad. And from here, we can pretty much just rip through the rest of the problem now that that's been identified. So we know that this is 1.5 amps. Because of the independent current source here. We know that this has to be 3 amps, which means that if we have 3 amps coming in and 1.5 amps coming in, that a total of 4.5 amps are coming in, so 4.5 amps have to be going out as well. So for this resistor down here, we know that we have V equals IR, and the current is 4.5 amps, and the resistance is 0.5 ohms. So the voltage drop across this resistor is 2.25 volts. Now because the current is coming in through the top, that means that this has to be the positive terminal on the top and the negative on the bottom, just like that. Now that 4.5 amps of current comes all the way around and enters into this junction here. So we have 4.5, and then we know that we have 3 amps coming up because of what we determined just above, and then this one has to be 1.5 as well, because of this independent current source forcing 1.5 amps through this branch. And then the voltage drop across this resistor is just V equals IR, which is equal to 1.5 amps times 6 ohms, and that means it's a total of 9 volts. So we can ground the circuit right here. You can ground it anywhere, but I'm going to choose here. When we look at this, we know that this is also the positive and negative, so this voltage drop is like that. So when we ground, we have 0 volts, and then when we cross this resistor, we're going to jump up 9 volts, which means everything on this side, this whole node, is going to be 9 volts higher than ground, so we can label that on as well. When we cross this resistor, we're going to jump up another 2.25 volts, so the next node up here is all going to be 11.25 volts higher than ground. And then when we come across this way, we're going to jump another 4.5 volts, so this whole node here is going to be 15.75 volts above our reference at ground here. So you can either recognize here that if we remember that this node up here is just 2.25 volts higher than this node down here, or you can apply Kirchhoffs' voltage law and go around. So we would have plus 2.5 volts. And then when we come into here, the only other element in this loop, it has to be negative 2.25 volts. Sorry, I should have said plus 2.25 volts and then negative 2.25 volts. So that would put the negative on this side and the positive on this side, or 2.25 volts. And then you can also see here that this one is 15.75 volts higher than this node. So obviously this has to be the positive side and that has to be the negative side. And the difference here is just 15.75 volts. Okay, so now we have all of the voltage drops. We know the voltages of all of the nodes, and we know the current flowing through every element. And we've checked that Kirchhoffs voltage law is going to be satisfied in both of these loops, and Kirchhoffs current law is satisfied in both of these junctions. So let's move on to finding the power dissipation of the resistors now. So let's start with the top one up here of 3 ohms, and we have power is equal to voltage times current. So we have 4.5 volts times 1.5 amps. That gives us a value of positive 6.75 watts. When we come down to the next resistor here, we also have the expression power is equal to VI, and we can write the whole thing. So we have 2.25 volts times 4.5 amps, and that gives us positive 10.125 watts. And then for the last resistor in the bottom left, we have power is equal to VI, which is equal to 9 volts times 1.5 amps. And that means that we have positive 13.5 watts. So when you sum all of those up together, we find that the total power dissipated by all 3 resistors together is positive 30.375 watts. Now what we should do is we should check the power delivered by the 2 power sources. When we're looking at this, the current is flowing into the negative terminal of both of them. So we're going to be putting in the current in this expression P equals VI as a negative value. Again, that has to do with the passive sign convention, and the link is in that video up in the top. But we can write the expression here. So we have power is equal to VI. Let's do the 1.5 amp independent source first. So we have the voltage across it, which is 15.75 volts times negative 1.5 amps, which gives us a value of negative 23.625 watts. And then when we check the power supplied by the dependent current source, it's P equals VI. And then we have, again, the voltage across it is 2.25 volts times negative 3 amps. And that gives us a value of negative 6.75 watts. So when we sum both of those together, we're just going to get a total of negative 30.375 watts. So the negative sign here indicates that power is being delivered, and the positive sign here indicates that power is being dissipated, and that's what we expect. These are equal and opposite to each other. So everything looks like we've done it correctly. We found all of the current flowing through each element. We found the voltage at each node, and the power dissipation and delivered by every element too.